Hello, it's me, Erin Debris. So we are going to talk about quantum time evolution today. Let's start with postulate 6. Let's start by asking what happens as time passes. Our book gives us postulate 6. The time evolution of a quantum system is determined by the Hamiltonian, or total energy operator, h of t, through the Schroedinger equation. Well, Schroedinger should have an umlaut here. Okay, now I'm happy. Of the Schroedinger equation, I h bar, the derivative with respect to t of psi of t is equal to h acting on psi of t for the state. So the Hamiltonian here is an operator. So here, h is the operator corresponding to the total energy. And it comes from the classical Hamiltonian, where h was equal to the kinetic energy T plus the potential energy V for a conservative system. More generally, if you've taken classical mechanics, you might remember that h is a function of the generalized coordinates q, the generalized momenta p, and also time. This is equal to the time derivative of the generalized coordinates dotted into the generalized momenta minus the Lagrangian of the generalized coordinates, the time derivative of the generalized coordinates, and time. Where p sub j, so the j component of the momenta, is equal to the partial of the Lagrangian with respect to q sub j dot. So the time derivative of the j generalized coordinate. So that's a little aside. If you haven't seen that yet, please don't worry about it. So then comes an important question here, which is how is the Hamiltonian h different from the energy E? This is an important question because the Hamiltonian here is the operator and E is the measured quantity. So we've seen this distinction before. We had an operator, SZ, that measured the spin along the Z direction. Spin component. I apologize for my spelling. It's always been terrible. Now, a short mathematical aside here. H is a functional. That is, H is a map from a vector space of functions, usually to real numbers. I mean, definitely to real numbers in this case. In plain language, H is a function that takes functions as its argument. So you put in functions and it returns a real number. So that's a little mathematical aside. Let's take a little bit more to ask ourselves a little more questions about this. One thing we can ask is, H is an operator corresponding to an observable. What properties do we expect H to have? This is a good question. We do expect it to have some properties, right? All right, so we do expect it to be Hermitian. This is one of the things that we learned in chapter 2. All observable operators are Hermitian. And all Hermitian operators have real eigenvalues. What will the eigenvalues correspond to? Well, these eigenvalues correspond to possible measurements of the total energy. So I can write down an eigenvalue equation for this mess. The operator H operates on the eigenstate, which I'm going to call E sub n. There's some energy eigenstates. This is the nth one. I don't know how many there are. This is a generic system. And it gives me the eigenvalue, E sub n, the energy of this particular state, times that state again. This was the eigenvalue equation, where E sub n is an energy eigenvalue. So a possible measurement that you could make of the energy. Let's combine this with the Schroedinger equation. Because H is Hermitian, we're going to figure out what this tells us about the eigenvectors or eigenstates. Because H is Hermitian, I know that its eigenvectors will form a complete basis. So I can write any state psi as a linear combination of all of these various eigenvectors or eigenstates. If this particular state, it may change in time, psi of t, in which case the constants themselves would be changing in time. Oh, I forgot to make a note here that we were going to deal only with time-independent Hamiltonians. Okay, so let's look at what happens here. We're going to look at I h bar. We're going to look at the continuous version, so treating this as a function with respect to time. This is equal to h times this function psi of t. So I can look at this and I can divide both sides by h bar. And this multiplied by psi is going to act on these different constants and will eventually give me, energy eigenvalues of various kinds. So I times the derivative of psi of t with respect to time is proportional to that same state psi of t. So now we're going to make a guess. I did quotation marks with my hands, which you can't see. Oops. So we're going to guess. Let's look at the function e to the I alpha t. Let's look at the derivative with respect to time times I of e to the I alpha t. So this is equal to I times the equation e to the I alpha t times the derivative of the stuff inside. I times I is -1. I'm gonna edit that out later. This is I squared alpha e to the I alpha t, or minus alpha e to the I alpha t. I can write this as the left term, the derivative with respect to time of e to the I alpha t. That is proportional to e to the I alpha t. When I say low for this looks like how psi behaves. Oh, that's good to know. That might be helpful. So this means that I'm going to write this back into my Dirac notation where this is some state. psi, and all the time independence is going to be in this exponential function because that corresponds to the time behavior of psi times some f, some state, which is time independent. We're not going to worry about it. H is also time independent. Let's have H act on psi of t. So this means that H is going to act on e to the I alpha t times this state f. Now we can write f, which is some state, as a linear combination of all the eigenvectors of H. So that means that this H times psi of t is equal to H times, now I'm going to write this system as the system over n of C sub n e to the I alpha n t times that particular eigenvector. Let's plug this into the Schrodinger equation. This is equal to psi, which is a function of t. So I have I h bar, the derivative with respect to time of the state of psi, which is the sum over n of C sub n e to the I alpha n t, where, I mean, this alpha n may be different for different states, who knows, times some eigenvector e sub n. And this is equal to the Hamiltonian acting on the state, which is the sum over n, C sub n, e to the I alpha n t times the eigenvector or eigenstate e sub n. That's where we are. Now, let us look at how this derivative depends on time. So note to self that the only time dependence is here, only t dependence. So this is the only term that the derivative is going to act on. All right, so I have this I h bar, which stays out. And I'm going to have this sum over n, my C sub n's, times my derivative e to the I, so the derivative of e to the I alpha n t with respect to time, times this eigenvector vector e sub n. This is equal to I mean, really, this is a derivative here. It should be not part of the psi system. The Hamiltonian, which is then multiplied by psi. Here. So let's look at this derivative here. Now, I'm going to do one of those fancy tricks. So this may, this is Fourier's trick, where you multiply by another state. So I'm going to multiply both sides by e sub k, but in the bra form here. So now I have this IH bar. That's just a constant, so it comes outside. I am then going to have the sum over n. I'm going to bring this e sub k inside because it doesn't matter. You can multiply each term by e sub k or after you add them together. Again, doesn't matter. E sub k, which is acting on C sub n times this derivative. This derivative, after I take the derivative, I get I'm going to get I alpha n e to the I alpha n t times my original state, or my original eigenstate, E sub n. So this is equal to, now here H is a Hamiltonian, it's an operator. Now the operator only acts on states. It's not going to act on this other stuff. So that means that I can bring this all into the terms. So it doesn't act on the C sub n or e to the I alpha n t. It just acts on the states. Okay, let's do a little simplifying. This part here, these are all numbers. They can come outside of the states when I do these weird inner products. It doesn't matter. The inner products worry about operators and states, and that's it. So I get this I h bar, and then comes the sum over all possible values of n, whatever that is, C sub n, I alpha n, e to the I alpha n t. And then it's going to be EK, inner product with EN. All right, so this then is equal to the sum over n, C sub n, e to the I alpha n t. And then I've got this crazy operator, EK, times the operator, the Hamiltonian, H, which is acting on the state, E sub n. So at this point, I am going to remind myself, and I say to myself, self, H is Hermitian. And we've set this up so that we have eigenstates. So this means that its eigenstates ENs, form an orthonormal basis set. I mean, that's what we're concerned about, right? So this means that if I have two of these states, EK, EN, that it is going to be equal to 0 if K doesn't equal N, and is equal to 1 if K is the same as N. This is also known as the Kronecker delta, which I indicate as delta Kn. So we've learned about the Kronecker delta, which tells me that this, for an orthonormal basis set, when I take the inner product, I either get 1 or 0, depending on if these are the same states or different states. Let's plug this into my equation, which was IH bar times the sum over n, C sub n, and then I had these extra products, I alpha n, e to the I alpha n t, and then that's where this inner product was. Now I'm going to replace it with this delta Kn. I say, fantastic, that's much simpler, I hope. Well, it's just ones and zeros, it's definitely simpler. And this is then equal to the other side, which was the Hamiltonian acting on stuff, C sub n, e to the I alpha n t. And then I had this ek, the Hamiltonian, acting on e sub n. Okay, well, I know, sorry, this is a sum over n. I know that this e sub n here, this is an eigenstate of the Hamiltonian, right? That was a choice. So that means I should get the eigenvalue back. E sub k times the eigenvalue e sub n times the eigenstate. Well, this is just a number, so it should come right out with all my other numbers, c sub n, e sub n, e to the I alpha n t, ek, en. I said, oh good, I put the Kronecker delta back in. Okay, let's rewrite this equation. I now have I h bar times the sum over n of c sub n I alpha sub n e to the I alpha n t times the Kronecker delta kn. This is equal to the sum over n of c sub n e to the I alpha n t times e sub n, the eigenvalue, times the Kronecker delta kn. And I say to myself, remember that delta equals 1 if k and n are the same, and if they're different, it's 0. So this is really just a sum of 0, 0, 0, plus some non-zero when k equals n, plus a whole bunch of other terms that are also 0. That's what the sum is. So I just need to be worried about this one non-zero element. So I'm going to have I h bar, and this when n equals k, which I'm going to write as c sub k, I alpha sub k, e to the I alpha sub k t times 1 is equal to, now I just have to worry about the k when n equals k for this term. So that's c sub k e to the I alpha k t ek. Now we are going to engage in my favorite part of math, which is the canceling of stuff. What stuff can we cancel? Well, we can definitely cancel this e to the I stuff. That appears on both sides. And we can definitely cancel this constant k. That appears on both sides. And now I have I squared h bar a sub k, alpha k, sorry, is equal to e sub k. Well, remember that I squared is minus 1. So this is minus h bar alpha sub k equals e sub k. Or, more importantly, alpha sub k is equal to minus e sub k over h bar. This is extremely important. Yeah, they did good work. So let's do a little bit of rewriting. This means that I can now write my psi as a function of t. Remember that it was originally some sum over n, c sub n. Sorry, let me move this. All right, and then I'm going to erase this bit. There we go. It was c sub n, e to the I alpha n t, e sub n. Now I can write this as psi as a function of time is equal to the sum over all possible values of n, c sub n, e to the I. Now alpha was, oops, I'm going to have a minus I, e sub n t over h bar time e sub n, where this is the eigenvalue of this a particular state. So this is how I can write how the function depends on time. And this means at t equals 0, psi of 0 is equal to the sum over possible values of n of c sub n e to the 0, which is just 1, times these various eigenfunctions. All right, so we are going to just stop here. There are lots of questions that we have, and we are going to look at them in class. Take care.